This is Math 154, Calculus 2, and we'll be beginning in our same textbook that we used for Calc 1, but in Chapter 6 where we left off. Chapter 6 is a very long chapter. There's lots involved, so I'm actually going to split it into 2 units. Unit 1 is going to be comprised of sections 6.2 through 6.6. We'll go back and grab 6.1 when we do the second unit. These are all geometric applications of the integral. So we're going to be calculating things like areas and volumes, geometry types of things within this unit. All right, so let's go ahead and get started. Section 6.2 talks about using integrals to find the area. We've started this process in Calc 1. You saw a little bit of this before, so I'm going to begin by just building on what we already know. If I would like the area between the graph of a function and a coordinate axis, this is like the area under the curve. And we saw back in Calc 1 that that can be calculated with a definite integral. So let's take a look. In our first example, we want to find the area of the region bounded by this graph and the x-axis. Now, as far as graphing is concerned, you're welcome to use your calculator to help you. I can see that this is an upside down parabola. If I put it in my calculator, -5 to 5 looks like what I got here anyway. And there we go. So I'm going to sketch what I see. It looks like the x-intercepts are 1 and 4. I can verify that as well. And looks like the vertex is somewhere around 3.5, or 2.5 rather, 3, 2.5, 2.5, right about there. And I'm just going to sketch in that upside down parabola. All right, so what I'm looking for is the area underneath that graph, or between that graph and the x-axis. So I'm looking for this area right in here. Okay. Just to be sure we've graphed it accurately, let's double check those x-intercepts. I saw on the graph it looked like they were at 1 and 4, but I can just set my y value to 0 to verify that. That would be x squared minus 5x plus 4 equals 0. And let's see, if I factor that, x minus 1, x minus 4, it does look indeed like x equals 1 and x equals 4. So, looks good here. This region lies between x equals 1 and x equals 4. When we do these problems, because they're going to get more complex as time goes on, what I'm going to always ask you to do is to draw what we're going to call a representative rectangle. A rectangle that you can imagine, like we did back in Calc 1, summing up a whole bunch of little rectangles to make an approximation to this area. We won't actually do the summing now. We're going to use the definite integral. But we'll draw just one representative rectangle. Something like this. If I drew a whole bunch of those, it would approximate the area under the curve. And I know that the area of my rectangle is the base times the height. Okay. We're going to set up by labeling this what the base and height are, and then we'll convert to an integral. The base of the rectangle is a little tiny piece of the x-axis. So I'm going to call the base delta x, a small section in the x direction. And my height here is actually a y value. It's the y value on my parabola, which is minus x squared plus 5x minus 4. So The area of a rectangle, base times height, would be delta x times minus x squared plus 5x minus 4. The total area under the curve is what I get when I'd add up, or as we now know, integrate, all of the possible rectangles. So the total area will be the integral of this, the function minus x squared plus 5x minus 4, and then the delta x becomes infinitesimally small, dx, when I try to fit infinitely many rectangles into that space. As far as my limits of integration, these x values start when x is 1, and they end over here when x is 4. And so that's my starting and stopping points. All right, I'm ready to go ahead and actually do this integral. That would be a negative 1/3 x cubed plus 5/2 x squared minus 4x, evaluated from x equals 1 to x equals 4. I plug in the top one first, so I'd have negative 1/3 times 4 cubed plus 5/2 times 4 squared minus 4 times 4. And then I subtract what I get when I plug in the 1. Plugging in 1, that's just going to stay negative 1/3 plus 5/2 minus 4. And then I just plug that into my calculator, and I got 4.5. So the area here is 4.5. Now, I know that I'm asking you to show me some things geometrically, and you probably could have set this problem up pretty easily without doing these labels, but I would like you to get in the habit of labeling your representative rectangles, because as I said, where we're going in this chapter, as the problems get more complex, you're going to find that that habit is going to really help you out later on. So we're going to start the habit now while things are still fairly straightforward. All right, let's try another one. In part B, we want to find the area of the region bounded by the graph of y equals ln x, the x and y axes, and then the line y equals 2. So y equals ln x. You may know what that looks like. If not, that's what you got graphing devices for, right? We've got a vertical asymptote here on the y-axis. Looks like the x-intercept is at 1. And then it just goes up slowly from there. Like so. All right. The two axes, the x and y axes, are also boundaries. And then the line y equals 2, this horizontal line here, is also a boundary, along with this y-axis and this piece of the x-axis. Gives me this sort of odd shape in here. All right, we're going to go ahead and try and find this area. And I do have an issue here. If I were to try to draw my representative rectangle exactly the same way as I did before, notice that I would be in trouble. Sometimes the rectangles would just be vertical right here between the x-axis and the line y equals 2. And other rectangles would go between the natural log curve and the line y equals 2. When I draw a representative rectangle, I want it to truly represent all of the rectangles that I could possibly have for the entire region. And I can't do that with a vertical rectangle here. So what I'm going to do instead is I'm going to turn my rectangle sideways. I'm going to draw it horizontally. Notice now, no matter where I draw the rectangle, it always starts on the y-axis and ends when we get to the natural log curve. Okay? So that's truly a representative rectangle. This time the base of my rectangle is this little piece of the y-axis. So the base I'm going to call delta y this time. And the height of the rectangle is lying sideways. So the height is actually this x distance. What I'm going to need to do is I'm going to need to resolve this equation for x because I need an x value for my height. This is going to happen every time you use horizontal rectangles. So instead of thinking of this curve as y equals ln x, I'm going to think of it as x equals e to the y instead. So my height is actually e to the y. Here's a little hint for you. The variable in your base and height should always be the same. So if they ever don't match, you need to go back to your equation and rewrite. All right, so I think we're in good shape. The area of my little rectangle, a sub r, is base times height. The base is delta y, and the height is e to the y. So the area of the full region that I want, I could get by integrating this function, e to the y, and again I'm going to shrink the delta y's infinitesimally small, so they'll become dy's. Now this time, y is the variable of integration, so my limits of integration need to be y values. And notice that those y values start here at 0 and stop here at 2. And so there's the integral that represents that area. Doing the antiderivative of e to the y, it's just e to the y. And that gets evaluated from 0 to 2. So I have e squared minus e to the 0, or e squared minus 1. That would be an exact value. Of course, you could plug e squared minus 1 in your calculator to get a decimal approximation of about 6.389. So this is going to become a question that we're going to ask ourselves over and over. For any particular region, one of the first decisions that we'll need to make is whether to use vertical or horizontal rectangles to set up our area function. All right, we're going to go up a step in complexity. Instead of finding the area between a curve and either the x or the y-axis, we're now going to look at how to find the area between two curves. Before I do that, let's just remember that, as we saw before, with the area between a curve and an axis, it's important to decide how your representative rectangle should be oriented, either horizontally or vertically. That's what determines the variable of integration. So let's take a look here. If I've got two curves like this one is f of x, and this upside down parabola is g of x, and my goal is to find this area in between them. I'm going to do the same thing I did before. I'm going to draw a representative rectangle. And it looks to me, if I draw it vertically, it's going to work out just fine. Notice that no matter where I draw it, it's always going to go from this bottom curve f of x to this top curve g of x. And that's consistent no matter where I draw the rectangle in the region. So the base of this rectangle is a little piece. It's not actually on the x-axis this time, but it is in the x direction. So I'm still going to call it delta x. And then I have to think about this height function. The height goes from the f of x curve to the g of x curve. So if I took the top y value and subtracted the bottom y value, I would get the distance in between them. My height here is the top, g of x, minus the bottom, f of x. So for my vertical rectangles, the area of the representative rectangle is going to be base times height. The base is delta x, and the height is g of x minus f of x. I can then use that to set up an integral that represents the whole region. I'm going to integrate this function, so g of x minus f of x, and then the delta x again shrinks infinitesimally small to become a dx. We're going to have to integrate between the intersection points of these two curves, which I'm just going to call A and B. So in general, anytime you draw a vertical rectangle, your little base is always going to be in the x direction. So when we make vertical rectangles, we'll always integrate dx every single time. All right, let's look at a situation with horizontal rectangles. Here I've got the function x equals g of y, and over here x equals f of y. And if I were to draw a representative rectangle between them, I'd want to draw it horizontally. Notice again, it always goes from the G curve to the F curve, right? If I'd done this vertically, I'd have been in trouble. Sometimes I would have gone between two parts of the G curve, and other times from the F to the dotted line. It would not have been consistent. So much better to go horizontally here. The base of my rectangle, the short side, is a little piece in the y direction. So I'm going to say the base is delta y. And then the height would be the larger x value minus the smaller. The way this one's written, f of y is on the right, so it's the larger, minus the g of y is on the left, so it's the smaller. So the area of my representative rectangle, base times height, my base is delta y, and my height here would be f of y minus g of y. Sorry, little pause to quiet the dogs down there. All right, so here's the area of my rectangle, and I can then integrate to find the complete area between the curves. We'd have our f of y minus g of y, and again the delta y will become infinitesimally small, so I can get infinitely many rectangles, and it becomes a dy. Here you'll notice that they've labeled these points C and D, where we want to stop integrating. They actually didn't go all the way to the intersection points this time. They must have told us in the problem where to stop, and that happens sometimes too. Okay. So anytime we do horizontal rectangles, the little short side, the base, will always be a little piece in the y direction, and we'll always end up integrating dy. All right, I'm going to write one more little generalization on the next page, and then we'll try some examples. Notice that when you did your heights, with the vertical rectangles, we always took the top minus the bottom. In order to get the height function. And with the horizontal rectangles, the larger x value was on the right, so we subtracted the right minus the left. And that's a good way to remember your height functions. Top minus bottom for vertical, and right minus left for horizontal. That is shown to you on the next page. As sort of a summary, when we are doing vertical rectangles, we always take top minus bottom to be our height function. And when we are doing horizontal rectangles, we always take right minus left to be our height function. All right, let's do some examples. In example 2, I'd like to find the area of the region bounded by y or f of x equals x cubed, and then y or g of x equals the square root of x. This specifically says to use an integral with respect to x. And so just as a reminder, they're really telling me to use vertical rectangles by saying that. But we should be able to do a little graph and kind of see what this looks like anyway. Now, one of the things I want to let you know is that I'm fine with you going ahead and using your calculator to draw graphs and even to find intersection points. Hopefully by now you're good enough to do those by hand if you really needed to, but we've got enough else to set up. You don't need to worry about finding the intersection points by hand. So, most of these you can do on a graphing calculator. Some of them are much easier on Desmos, so I'll show you both, but I know that you probably have more access to graphing calculators than Desmos, so I'll mostly demonstrate that way. All right, so let's see. In this case, my two curves are y equals x cubed and y equals the square root of x. My window is set up as -5 to 5. I'll leave it until I see what's going on here. And let's see. Looks like I'm talking about that little tiny piece right in there. As a matter of fact, it's such a small piece that's between the two curves, I'm going to go ahead and change my window. Let's just go from -2 to 2. I think that's going to be enough. Oops, said -2 to 2. Let's see if I can type it. There we go. That's a little bit easier to see. So I'm going to go ahead and start by sketching that. And this intersection point right here, I can find that using the second calc intersect. First curve, second curve, and I know 0, 0 is that intersection point. It's this one that I'm interested in. And it is 1, 1. So let's see, 1, 2, 3, 4. Let's call this 1. 1, 2, 3, 4. We'll call that 1. And that's where my graphs are going to intersect. The square root curve just looks like that. That one's what we call g of x, or just y equals the square root of x. And the other one, the cubed graph, y equals x cubed. Look like this. Like so. All right. My goal then is to find the area of this region between the two curves. And I was specifically told to do this using an integral with respect to x, meaning I need vertical rectangles. So I'm going to sketch my representative rectangle vertically. And I can see that the base is a little piece in the x direction, so delta x. And the height, I'm thinking top minus bottom here. The top is the square root of x minus the bottom is on the x cubed curve. So the area of my rectangle, base times height, is the square root of x, is the delta x times the square root of x minus x cubed. The area of the entire region is going to be the integral of this area, square root x minus x cubed, and then the delta x becomes the differential dx. X is my variable of integration. That means the limits of integration are the x values. And so I'm going to start here at x equals 0, and I'm going to end here at x equals 1. Now, hopefully you have gotten pretty good at doing integrals or antiderivatives. And so I'm going to say we'll do a couple of them by hand like we did the first ones. But in general, when we get to this point, we've got the setup, we will start using our calculator to do more of the routine integration itself. It's the setup that I'm most interested in here. So I'm just going to finish this one out by going into my math menu. And option number 9 is that integral. And that goes from 0 to 1. And we're integrating the square root of x minus x cubed dx. And I get about 0.417. Okay, so what I'm really looking for here is the geometry, that you've been able to draw the graph and show me the representative rectangle, how you found the base and height, and then the final actual integration step. Mostly you'll be able to do them by calculator. A couple of them I'll ask you to do by hand, but in general we'll speed up the process a bit by using the calculator. All right, now I'd like to read you the same problem, but this time I'd like to use an integral with respect to y. Since I'm finding the same area, I really do need to get the same answer. Hopefully I will. But let's go ahead and set it up and see what it would look like. So my picture hasn't changed. It's the same area. Intersection point at 1, 1. And here's that square root graph. And here's the x cubed graph. All right, because I was told to use an integral with respect to y, I know that I need to use horizontal rectangles. So I'll sketch in my little representative rectangle here. And that way my base is that tiny little piece in the y direction. So the base is delta y. The height, I'm going to have to go with the right side minus the left side. And that means that I'm going to need x values. I'm going to need these solved for x. Every time you do horizontal rectangles, you always need to solve your equations for x. So I'm going to say this one, if I solve for x, I'm going to think of it instead as x equals the cubed root of y. And this one, if I solve for x, x would equal y squared. Now, the right side is on this blue curve. That was the cubed root of y. And the left side is on the square root curve, which is now y squared. So, the area of my rectangle base times height is the base delta y times the height cubed root y minus y squared. By the way, at this step, you can always double check and make sure, notice that your variable should be consistent. Everything here is y's. If I've got a mixture of x and y's, I need to go back and probably resolve my equations. I've got a problem. Okay, so the area function then, I'll turn into an integral to get the area of the whole region. And it's going to be cube root of y, or I might want to write that as y to the 1/3 just because it's easier to type in my calculator, minus y squared. And then the base delta y becomes a dy when there are infinitely many of them. This time, y is the variable of integration, and so I need to look on the y-axis for my limits. 0 is still my lower limit, and 1 is actually still the upper limit, but notice that I'm looking at the y value of 1 this time when I determined that. All right, moment of truth. Let's see if we get the same answer when we integrate that in the calculator as we did before. All right, I'm going to go from 0 to 1. And even though I know these are y's, in the calculator I'm going to have to type x. So I'll type x to the 1/3 power. Doesn't really matter what variable we use, the answer will be the same. Minus x squared dx. And even the calculus, think a minute, there it is. And notice we get the same answer, 0.417. There's a little bit of difference out here at the end. That's just kind of round off error. The calculator has to use a numerical value to do this as well. So I'm convinced those really are the same. All right, let's do a few more examples. In example 3, we're looking for the area of the region bounded by y equals x plus 2 and x equals 4 minus y squared. Now, if you only have access to a calculator, you can do this on a calculator by solving this for y. And I'll show you how to do that in a minute. But I do want to mention that if you have access to a computer and you can use Desmos, it's really nice because Desmos allows you to type in the x equals equations. You don't have to solve them for y. So I'm just going to pop over here for a moment and do this one on Desmos for us. Let's see, I may have to make this a little bit smaller. There we go. So, my first equation was y equals x plus 2. Just go ahead and type that in. That line. My second equation was x equals 4 minus y squared. The parabola. And not only can I clearly see the region that I want, but I can even find the intersection points just by clicking. That intersection point is at 0, 2. And that one's at -5, -3. So kind of nice. All right, so there's my graph, and I'm going to go back to our paper. I've actually just sketched the same graphs that I just saw on here with those intersection points. There's that 0, 2, and this one was at -5, -3. And this is the region whose area I'm trying to find. By the way, if you don't have access to Desmos and you are graphing on a calculator, you can generate the same graph. You would, of course, use y equals x plus 2, and then for this one, you'd have to solve it for y. So you'd have y squared equals 4 minus x, and y equals plus or minus the square root of 4 minus x. So you'd have to graph three things, y equals x plus 2, and then both the positive square root equation and also the negative square root equation. So it takes a little bit more work, but it's certainly doable on a calculator. Again, just for helping us to move through these a little bit more quickly, I'm going to go ahead and use Desmos for graphing when I can, but just know that if you don't have access, it's still possible to do these problems. All right, I need to make the decision between horizontal and vertical rectangles. And the first thing that I'm going to notice is if I try to go vertically, there are times where I'm going between the parabola and the line, and there are other times where I'm going between the two branches of the parabola. So a vertical rectangle is not going to give me a consistent representative rectangle. I'm better off going horizontally. Horizontally, I'm always going from the line on the left over to the parabola on the right, no matter where I draw it. So we'll choose the horizontal rectangle this time, and I'll notice that the base is a little piece in the y direction, so that would be delta y. And the height is this horizontal, it's really like a length of the rectangle. And so I'm going to go with right minus left. And because I'm doing horizontal rectangles, I do want the x equals form. So let's go ahead and write those down. For the parabola, I already have the x equals form. This was x equals 4 minus y squared. But for the line, I need to solve this for x. X would be y minus 2. So when I look at my rectangle here, right minus left, the right side is on the parabola. That would be 4 minus y squared. Subtract the left side, which is on the line, y minus 2. So I'm going to say that the area of my representative rectangle, base times height, is the base delta y times the height, 4 minus y squared, and I might as well distribute this, minus y plus 2. Or I could even simplify a little bit further, minus y squared minus y plus 6. Okay, I'm now ready to write down the area of the complete region. I'm going to need to integrate the area function from the rectangles. Delta y becomes dy. And since y is the variable of integration, I need the y values as my limits of integration. This point down here is at a y value of negative 3. And this intersection point up here, of course, has a y value of 2. Again, it's not difficult to do that integral by hand, but just to make things a little faster, we'll put it in the calculator. And I get 20.83 approximately. By the way, when you have a pretty obvious repeating decimal like that, remember that your calculator can give you an exact answer as a fraction. This is exactly equal to 125 over 6. Especially when you do problems in the book, they often give exact answers, so that's just a useful little hint to know. All right, let's go ahead and try, I think we'll do 2 more here on this video, and then we'll take a pause and start a new one. Let's do this part B. This time I want the region bounded by the graph of y equals 1 over the square root of 1 minus x squared and y equal 2. So let's see what we've got here. I am once again, just because I think it's such a nice feature, these aren't hard to graph on the calculator, but it's so simple to find things on the Desmos. I'm going to go ahead and do it that way. So let's graph it on Desmos. I've got y equals 1 over the square root. I've got to go ahead down here and get into my little menu system to get my square root of 1 minus x squared. And then I've got y equal 2. All right, got my picture over here, and I can see it's really just this little region in here that I'm interested in. If I want to, I can fix my window using this little wrench up here in the corner. Don't really need that much. Let's just go like -3 to 3. On the x-axis and also on the y-axis. Oops. There we go. And now I can really see my region. The intersection points here are 0.8662 and -0.8662. So I'm going to go ahead and transfer that over to a graph on the paper. Okay, here we go. So here's that kind of, not really a parabola, but sort of similar to one. And here's that horizontal line, y equals 2. And my goal is to find the area of this region in here, between them. This time, I don't see any reason not to use vertical rectangles. Every vertical rectangle will go from this curve up to the horizontal line. And that way, I don't have to try and solve this for x, which would be kind of a pain, right? It's probably better to do the horizontal rectangles. All right, the base is a little piece in the x direction, so delta x. And the height, I'm going to go top minus bottom. Height equals top minus bottom. The top is just the horizontal line y equals 2, minus the bottom, which is the curve, 1 over the square root of 1 minus x squared. So the area of my rectangle, base times height, is the base delta x times the height, 2 minus 1 over the square root of 1 minus x squared. To get the area of the whole region, we then have to integrate all of these rectangles together. And to put this into my calculator, it would probably be a little bit easier if I just wrote that as 1 minus x squared to the -1/2. The delta x becomes a dx. And then I'll notice this is x values in my integral, so I need x values for my limits of integration. We had written down, or I wrote down rather, the x values, or the whole points actually, of intersection that we found using Desmos. So I'm going to use the -0.866 and the positive 0.866, the x values at those points of intersection. We can then just go to our calculator and get a final answer. And that's about 1.3697. I'm not seeing any really nice repeating decimals or anything there, so I don't think that I would probably get anywhere if I tried to convert that to a fraction. What usually happens is it just gives me the decimal back when I try, when there's no nice fraction to be had. All right, one more. This time I'd like the area of the region in the first quadrant, bounded by x squared plus y squared equals 16, y minus x equals 0, and the x-axis. We've been performing our integrations on the calculator, but it even specifies to do so this time. This is one I kind of hope you recognize. That's just a circle of radius 4, right? If you don't, we can get it on Desmos, and I am going to go show it to you there as well, but let's sketch this one first. I think we can do it on our own. Let's see, circle of radius 4, 1, 2, 3, 4. Like so. And then this is really just y equals x. And so that's just the line through the origin with slope 1, that perfect diagonal. And I just want the part in the first quadrant. And again, I only wanted the part in the first quadrant. So I'd be looking at this piece right here. All right, so the question that I hope is now becoming familiar. Do we want to use horizontal or vertical rectangles? This is one of those times where the vertical rectangles wouldn't be representative. Sometimes they go between the x-axis and the diagonal line. Other times they would go between the x-axis and the circle. So vertical rectangles aren't going to work as well this time. Let's go with horizontal. Notice that every horizontal rectangle will run from the line to the circle. So that's perfect. All right. This means that my base is a little piece in the y direction, delta y. And my height function, I'm going to go with right minus left. Okay, since it's a right and a left, those are x values, I am going to need these equations solved for x. The line's simple enough, that's just x equals y. And if I were to solve the circle equation for x, I would have x squared equals 16 minus y squared. So x would be, and I'm just going to put the positive square root of 16 minus y squared, because everything I'm doing is in the first quadrant, so I'm only looking at positive x values. So that's the equation of my circle. X equals the square root of 16 minus y squared. All right, right minus left. The right side is on the circle, so that would be the square root of 16 minus y squared, minus the left side, which is on the line. That's x equals y. So the area of my rectangle, base times height, is delta y times the square root of 16 minus y squared minus y. That means the area of the entire region that I want would be the integral of the area of all the little rectangles, square root of 16 minus y squared minus y, and the delta y becomes my dy. And because these are y values, I need the y values for the limits of integration. Clearly we start here at y equals 0, but I am going to need the y value up here at that intersection point for my upper limit of integration. Okay. I've gone ahead and I've actually graphed this already for us on Desmos. There's the circle, x squared plus y squared equals 16. There's the y equals x line. And there's the intersection point, about 2.828, actually for both x and y, but it's the y value that I'm interested in right now. So this is 2.828. For my upper limit of integration. And then it's just a matter of putting this into the calculator to get a final answer. Again, I do have to use x's in the calculator when I integrate, but what variable we call it really doesn't matter. And I'm getting about 6.283. I'm a little suspicious here. That sure looks a lot like 2 pi to me. And indeed, it looks like it is. So I think the actual exact answer is probably 2 pi. All right, let's pause there, and we'll come back and do a few more in the next video.